After we discuss about the big O notation, let's take a look at the examples as well as the programs to really understand what is the meaning of the big O notation, as well as how do we look into the program and understand or analyze the big O notation. Let's start with the easier one, which is the search problem. Here is the definition of the search problem. So given an integer x, this is our target, and an array of A, this is our search space. So inside of the array, we want to find the value of x. Once we found it, we want to return the position of x, which means the index of the A, or an indication that that is not available. It is not there. So because it's a possibility that x is not inside of the array A. So if x occurs more than once, here is some special case. So saying that the value you want to find appears 2 times in the array of A, as long as you return any occurrences, any one of that is considered as the correct position, and this array A is never altered. So this is a very straightforward searching problem. You will understand that you basically need to write a for loop or a while loop to go through each positions of A and then find for x. So here is a very straightforward example with only 10 elements over there, saying that array A is this array. It has from 0 to 9 index, and there are 10 elements inside of it, and x is equal to 5, indicating that is the elements that we want to find. It is pretty straightforward that we basically need to write a for loop, go through each items until we find the index, or we find the value of 5 and then report the index of 7. So basically the answer for this question is going to be 7, which is the index of element 5. You can see that in the next example, there are similar array, but it has actually x equals to 4, indicating that there are 2 index of 4, 4 values, and basically we return any location. Index of 1 is correct, index of 8 is also correct. So this is a very basic sequential search problem. So a sequential search that goes through the data sequentially until a match is found. So basically, if you have 10 elements, you need to walk through all 10 elements. If you have 100 elements, you need to walk through about 100 elements or until you find it. A sequential search is useful when the array is not sorted. So whatever kind of array they have elements over there, you just search one by one. Basically, here is some more detailed analysis. If it is an unsuccessful search, so basically you need to go through all positions and then report that it is not there. In the worst case scenario of the successful search, which indicating that the element goes in the very last location, so you still need to search every single one until you find it. The best scenario is that the element you want to find located at the very first location. So in the average scenarios, you basically have opportunity 50-50 to find it, so that you basically have half of n times to solve the problem in an average case scenario. No matter what, you can see that after we analyze the big O notation, it is going to give us a linear problem. Let's see something differently. Saying that we have the same problem, which again is try to find the value of x in an array A, and you want to report the index of the x. Saying that this time the array is sorted. So in this case, what we will be able to see is that we can do something else. We basically, because we know it's sorted, if we look into the middle of the array, we can basically understand the value of x is going to be on the left side of the array or on the right side of the array. And we will be able to minimize the search, which is saying that if it's on the left side, we don't need to search on the right side. So what we are going to do is that we try to use 2 values. One is the lower end, which in the beginning would be the leftmost position of the array, and the high end, which is the rightmost position of the array, to indicate where is the elements that we want to search, what is the portion of the array that we want to search. So If low end is larger than high end, we know the item is not there. This gives us a special scenario indicating that if the element is not there, we have a mechanism to find it. We will have some slides or some examples to look on these indications. So let's take a look of an example. Say we have a binary search problem. Now, the array is still array with 10 elements. The only difference is that they are sorted now. So the element 2, 3, 7, 9, 11, 16, 17, 18, 20, and 21, saying that the x that we want to find is 16. So how do we do that? We basically want to have a method to go through the middle of the element and then try to find the value. So we're still having the same situation. We want to get the return index of 5 and then indicating that that is the position that we have stored it. So we use the lower end as well as the high end, indicating first of all we want to search every single item. The range of the elements that we want to search is the whole array. So we have the low starting with 0 as always, and high indicating that the highest index of the array. So what we are going to do next is that we use this low and high to find out the middle index. Now, here's the tricky question. If my low is 0, high is 9, and we want to find the average of the two values, which means that if we try to say 0 plus 9 first, and then divide it by 2, what is the value? You need to understand we are talking as a computer. So if 0 plus 9 parentheses divided by 2, since every single digit of the numbers are integer, then we will actually get an integer division. So it's not going to give you a 4.5. It will give you a 4. So that's indicating the middle index is 4 in this case, and that is the middle location we want to look for. So if we get the middle index of 4, understanding the value is 11, compared with our x, which is 16, we know that the element need to be on the right side of the array. So what we will do is that we will move our low index to the middle index to the right side of it. So it will be middle plus 1 will equals to our low index. So it will change my low index equals to 5, high index equal to 9, indicating that these are the range of the elements that we want to search. On the other words, is basically the right side of the middle index. Let's take a look at this. So we compare the value stored in the middle index, and basically when we doing that, there are three possibilities. One is that the value in the middle index is less than x. The case 2 is that the middle index is greater than x. And if it is not less nor greater, that's indicating the middle index is equal to x. So that is our answer. Basically, this is our best case scenario that we want to get. Of course, looking into this slide, you understand this is a if-else-if problem. So you can see that once we have finding out this scenario, if the value in the middle index is less than x, then we search for the right side of the middle index. If the value in the middle index is greater than x, now we know that we need to search on the left side because x is less than the middle value. If it is not greater, not less, then we found it. So all we need to do is return the middle index. So you can see that if we go through the approach, the same problems as we see earlier, the middle index now it gives us an index of 4. We compare 11 with 16. Understand that we need to search on the right side. So what we will do is that we will change the low index to the middle plus 1 equals to 5. So you can see that in our next slide, we change our low index to 5 and our high index still stays not changing. That's indicating we want to search these elements. And when we do that, we will repeat the same process. finding the middle index of the low and high, which again 5 plus 9 divided by 2 will give us an index of 7. So now compare with the value stores inside of the index of 7, 18, with the value of 16, we know it's going to be on the left side. So what we are going to do is that we need to change our high index to the middle index left side. So what we will see is that we will change our high index to middle minus 1 equal to 6. In this case, we have our low and high index stores at 5 and 6. When we're doing that, finding the middle value middle index between 5 and 6 is 5 plus 6 divided by 2 equals to 5. So what we will get is that we will understand 16 is equal to 16, and we hit our third case scenario, so we can basically report an index of 5. And therefore, if we look into the program, you see that to initiate everything, we said low equal to 0, high equals to a.size minus 1. This a.size is available because we using what we call something called vector. At this stage, you can image that vector is another or advanced version of an array. So you can see that it's the same thing with an array, but vector will be able to support some functionalities. In this case, we use a.size to get how many elements that we have inside of the vector, minus 1 indicating we want to get the highest index because we're starting with 0. In this case, once we have initial low and high indexes, so you can see that what we are going to do is that we basically calculate the middle value. So you can see that we calculate the middle value over here and then look for 3 different cases as I mentioned earlier. In here is a very nice part. That's the part I mentioned earlier we will discuss here. Is indicating that while low is less or equal to high, we always want to make sure low is on the left side or at the same location of the high value index, so that we will keep searching. If that's not true, then we will stop searching. Let's take a look of this example. Saying that this is this array of A, you can see that a sorted array. Now we change our x equals to 8, indicating that it is basically not there. So we want to know how does the program will be able to tell that 8, the x is not in the array. So the program will return not found. Let's try to see how do we do that. 0 index and high index, finding the middle value equals to 4. Compare 11 with the value of x, which is 8. Understand it's on the left side, so we need to move our high index to the left side of the middle index. You can see that we threw half of the elements away by doing that one comparison. And when we do that, low and high is 0 and 3. Finding the middle index is 1. Compare 3 with 8. We know that the elements we want to find is on the right side of the middle index. So we will change our low index to 2, high index to 3. Finding the middle value, which is going to be 2. And then we will understand that the value that we want to find is basically we change our low to our middle plus 1 equals to 3. So at this stage, you can see that we will move our right side, we will move our low to the right side of the middle index. Now, low and high are pointing at the same location, that's fine. Because if the x we want to find is 9, this is where we can find it. However, because the value we want to find is 8, so you can see that in this case, we found when the comparison of a of 3 equals to 9, which x equals to 8, we know we need to search the left side of the middle value. So that is when we will change our high to the left side of the middle index, which is equals to 2. And that will give us a special scenario indicating that our low index is greater than high index. And that is when we can stop the program, indicating that this is not there. So that gives us a mechanism to see that if the element does not exist. And of course, that comes in the program that if it's not there, then we will return not found.